Good morning, everyone. Myself Ananya Sinha, roll number 205070. The topic for my presentation is Stability of Equilibrium and Virtual Work. So, first of all, we will discuss about stability of equilibrium. So, what is a stable equilibrium? A body is said to be stable when it slightly displaced from the position of equilibrium. The forces acting on the body tend to bring it back to the position of equilibrium. What is an unstable equilibrium? A body is said to be an unstable if, when slightly displaced from the position of equilibrium, the forces acting on the body tend to move it still farther from the position of equilibrium. Now, with now some points to remember. In stable equilibrium, the center of gravity of body lies on the vertical through the point of context and is below the geometric center. Wherein in stable equilibrium, the center of gravity of body lies on the vertical through the point of context and is above the geometric center. Then third, in the case of neutral equilibrium, the center of gravity of the body coincides with its geometric center. Now, how to determine the nature of stability? Let Z be the height of center of gravity of the body from the point of contact. Now first, express the height z in terms of variable theta. The position of rest is given by dz by d theta equals to 0, which on solving gives theta equals to theta 1, theta 2, and as position of equilibrium. Then next, the equilibrium is stable if theta equals to theta 1, if d2z by d theta is greater than 0 for theta equals to theta 1. The equilibrium is unstable at theta equals to theta 1 if d2z by d theta square is greater than 0 for theta equals to theta 1. If d2z by d theta equals to 0 for theta equals to theta 1, then we considered d3 by dz by d theta cube and d4 dz by d theta 4 for position of rest. D cube z by d theta cube equals to 0. The equation is stable or unstable. Now, some general conditions for stability of a body resting in one another. At the right hand side, a diagram is made where the upper body is kept on the lower body. Here, G is the geometric center from the point A. R is the radius of upper body. Capital R is the radius of lower body. H is equals to AG as shown in the figure, which is the height of CG from the point of contact. Now, the equilibrium is stable if 1 by H is greater than 1 by small r plus 1 by capital R, and unstable if 1 by H is less than 1 by small r plus 1 by capital R. Now, here are some particular cases which we have to remember. First one is if the lower surface is concave instead of the convex near A, then R is negative and the equilibrium is stable or unstable according as 1 by H is greater or less than 1 by R minus 1 by capital R. If the lower surface is near A in plane, then R is infinite and equilibrium is stable or unstable according as H is less than R or H is greater than R. The third point to remember is if the upper body has a plane surface in contact with the lower body, then R is infinite and the equilibrium is unstable or stable according as H is greater or less than capital R. Now, here we will discuss a question. A uniform beam of thickness 2b rests symmetrically on a perfect rough horizontal cylinder of radius A. Now show that the equilibrium of the beam will be stable or unstable according as B is less than or greater than A. Now first we will draw the diagram. Here the horizontal cylinder is resting on the beam. Then the height of CG of the upper body from point of contact A, which is H, is equals to B. The radius of upper body, which is flat, small r, equals to infinite, and radius of lower body, capital R, is equals to A. Hence, the equilibrium will be stable or unstable according as 1 by H is greater than 1 by small r plus 1 by capital R, or 1 by h is less than 1 by small r plus 1 by capital R. That is 1 by b is greater than 1 by a, or 1 by b is less than 1 by a. That is b is less than a, or b is greater than a. Now another question, a hemisphere rests in equilibrium on a sphere of equal radius. Show that the equilibrium is unstable when the curved and stable when the flat of the hemisphere rests on the sphere. Now here two cases will arise. The first case will be when the curved surface rests on the sphere. So here it is shown in the figure that the curved surface is resting on a sphere where G is its geometric center. Now H will be equal to AG and A minus 3A by 8, which will be equal to 5 by 8 by H. Now radius of upper body, which is small r, equals to A, radius of lower body capital R equals to A. Now 1 by capital R plus 1 by small r will give us 2 by A, and thereby 1 by H will be equal to 8 by 5A. Now 8 by 5A will be less than 2 by A, that is 1 by H is less than 1 by small r plus 1 by capital R, hence the equilibrium is unstable. Now case 2 will arise where the flat surface of the hemisphere rests on the sphere. Here H will be equal to AG, which will be 3 by 8A. 3A by 8, then R will be infinite and capital R will be A. Now adding up on, we will get 1 by A, where we will be seeing that 8 by 3A is greater than 1 by A, which gives us 1 by H is greater than 1 by R plus 1 by capital R. Hence the equilibrium is stable. Now moving on to our next topic, which is virtual work. When a number of forces act on a body and a body undergoes some displacement, then some actual work is done by the forces. But if the body is in equilibrium under the action of number of forces, then there is no displacement and hence force do not work. But in the same statical problems, we suppose that the body undergoes some virtual displacement which will be imaginary. In such cases, the work done by forces on the body will undergo a virtual displacement, which is known as virtual work. Now, principle of virtual work for a system of coplanar forces acting on a particle. The statement says that the necessary and sufficient condition that a particle acted upon by a number of coplanar forces will be in equilibrium is that the algebraic sum of virtual work done by the forces in an arbitrary small virtual displacement is 0. Now, forces which can be omitted in forming the equation of virtual work, or in simple words, the forces which will be neglected. Now, first is the tension of an inextensible string, the thrust in a light rod, reaction R of any smooth surface with which the body is in contact, mutual pressure between two bodies in contact, reaction at a fixed point or a fixed axis about which the body rotates, reaction at a place of point of contact with fixed surface on which the body rolls without sliding. Now, tension of a string, the virtual work done by the tension will be minus T del L. Then the thrust in a rod will be T del L. Now, what will be the method for solving the problems? First, we will draw the figure and mark the forces. Then replace the string by the two forces acting inwards, and if it is length L, then the virtual work done by the tension of the T of the string will be minus T del L. Then the third case, replace the rod by the two forces T and T acting outwards, and if AB of length L be the virtual work done by the thrust T of the rod, then it will be T del L. Then mark the position of application of various forces and measure their distances from the fixed point or fixed line. Now the thing to remember is that, or a note, if the distances of various points from a fixed point on the line are measured in the direction of force, then the work done will be positive, and if they are measured in the direction opposite to that of the force, then the work done will be negative. Now we will come up with a question, which is 4 equal heavy uniform rods are freely jointed so as to form a rhombus, which is freely suspended by one angular point, and the middle point of two upper rod are connected by the light rod so that the rhombus cannot collapse. Prove that the thrust of this light rod is 4w tan alpha, where w is the weight of each rod and 2 alpha is the angle of rhombus at the point of suspension. At the right hand side, we have drawn a diagram where a rhombus is freely jointed, where 2a is the length of each rod. It is marked as A, B, C, D, and the thrust is marked as TT. Now let T be the thrust and the rod EF joined in the middle points of AB and AD. Let 2A be the length of each rod. Now AO will be equal to 2A cos alpha. KF will be equal to A sin alpha, where EF will become the twice of KF, which will become 2A sin alpha. Now the equation of virtual work will become as 4W del OA plus T del EF equals to 0. Now putting the equation 4W del 2A cos alpha plus 2 del 2A sin alpha equals to 0. Now we will partially differentiate it. We will get it as minus 8W sin alpha plus 2AT cos alpha within bracket alpha del alpha equals to 0. Then it will become as minus 8w sin alpha plus 2at cos alpha equals to 0. On further solving, we will get t equals to 4w tan alpha. Now next question is, four uniform rods are freely jointed at their extremities and form a parallelogram ABCD, which is suspended by a joint A and is kept in shape by the string AC. To prove that tension of the string is equal to half of the whole weight. Now firstly we have to draw the diagram, and it is on the right hand side where A, B, C, D a parallelogram is given and G is its center, W is the weight. Now capital W is a whole weight, T is a tension in the string. Now equation of the virtual work will become as W del AG minus T del AC. Now AG will be X, and if AG is X then AC will be 2X. Now putting the value of AG and AC in the equation of virtual work, we will get this as W minus 2T del X equals to 0. Now W minus 2T equals to 0 and W will be equal to half of, now T will be equal to half of W. Thank you.